Hi, hello. Welcome to my demonstration on differential calculus. Now today we're going to discuss all about graphs and derivative analysis techniques. Now let me try to ask DeepSeek what his opinion about the topic. Now immediately after that, he will reply to us, or he will prompt that it involves first and second order derivative tests as essential tools. Now let me try to discuss the first derivative test first. Now it involves finding critical points. Now, in order for you to do that, you must set the first derivative to 0, or the first derivative does not exist. Now, you will remember that the first derivative is essentially a slope of the tangent line to the curve. Now, if the slope or the slope of the tangent line is positive or greater than 0, you can picture out that the curve there in the vicinity is increasing. Similarly, if the slope or the first derivative there is negative or less than 0, you can picture that the slope, that the curve there is essentially decreasing. Now, for you to have a better idea, let me try to draw the actual curve and the corresponding first derivative, or the slopes near the areas. Now here, so let me try to write first derivative test. Now, what he means here is, what the AI mean is something like this one. So we have a curve here. So let me try to assign this as xn at that point. So let us try to examine also the tangent line. So we draw a tangent line here. It's relatively flat. And we have a function value. By the way, this is the x and the y axis. It has a function value f of xn. Might as well set the origin here to 0. Now, as you can see, the slope is flat, or the first derivative there is 0 because you have a flat slope. So f prime at xn is numerically equivalent to 0. Now let's try to examine the derivatives to the left and right of the point xn. So to the right, let me denote this. Let us agree on the point xn plus 1. And to the left, might as well assign it as xn minus 1. So here we also have a function value at those points. So here, let me try to assign this as f of x n minus 1, and there is a corresponding tangent line here. Now let me denote that as f of x n minus 1, but this time that's the derivative, and the slope of that, or the value, should be increasing, and it is greater than 0. So here, the profile of the curve is increasing. However, here in the right side, we can also draw a tangent line. Now the tangent line, it is obviously it has a value that is less than 0, simply because, as you can see, the function or the curve itself is decreasing. So decreasing. So in order for us to have a smooth transition from a positive or greater than 0 derivative positive to negative. So here, from left to right, we have a transition from positive to negative. So as you can see that the tangent line is essentially flat, or the first derivative is 0. So here, the first derivative at the point of consideration is xn. That is 0. Hence, that is a critical point. And corresponding to the critical point, we have a local maximum. So that's the condition. Now the second condition, you can picture that in your mind. Let me try to draw in another on the notation. That's xn, and to the right we have xn plus 1, and to the left we have xn minus 1. So again, we assign the function values. So this one is f xn. You'll notice that the f of xn is lower compared to the other values. So this one is f of x n plus 1. And then again, we try to draw a line that is tangent to the point at xn, and then assign the slope of that as 0. So again, this is the x and y axis. So as you can see, to the right we can draw a tangent line. As you can see, the slope of this time it is positive. So at f of x n plus 1, the first derivative there is greater than 0, the slope is positive, and as you can see, the graph or the function itself is increasing. However, to here to the left, we can draw another line, and we can say that the function value of the first derivative at xn minus 1, this time that is negative, simply because you can notice that the curve here is decreasing. So in general, if you want to go left to right, so from a negative, so the derivative there is negative, or the slope is negative, to a slope which is positive, you have no choice but to undergo or to move to us from the transition will move smoothly if you will go through a value of the first derivative to be again 0. And hence, we have assigned another critical point. And associated to the critical point here, is obvious that all other points are higher, so our point there is a local minimum, and all other points are higher compared to it. Now, we have successfully verified that if there's a change in the first derivative from positive to negative, then a critical point, or a value where the first derivative there must be 0, will give you the local maximum. And similarly, or conversely, if we go from the first derivative, we'll have a transition from a negative to positive, then it has no choice to pass through a value which is again 0, and that's the critical point for the first derivative at xn. Hence, we have a local minimum at xn. So here we have verified the claim for the first derivative test. In the next videos, I will give more examples, or an actual function, and we will try to apply the first derivative test to have an idea of how to plot the graph. But for now, that's all, and thank you.